All right, so here's the last bit of Newton's laws of motion. Here we're going to bring it all together, everything we've been working up to. Let's talk about dynamics, okay? So remember, when we reference our duck-on-pond physics, we're talking about dynamics as being below the water, where acceleration is that line of where the water is, okay? So this area of physics is often referred to as dynamics. Right, this is our putting it all together. Now we're making that connection between kinematics or motion, right? So that one-dimensional motion and forces. So we're putting it all together. Take these two, they combine into dynamics, okay? Now the quantity that connects the two, again, is acceleration. So if we refer back to our duck on a pond, right? So here's our duck sitting on this pond, right? Above the water, kinematics, right? Below the water, forces, okay, right? And then the water line, acceleration. So our duck represents our dynamics, okay, above, kinematics, below, forces, and then the water, the water line is acceleration. So sometimes you may start under the water and go up, right? Start under, go up, excuse me, above the water, or you start above the water and you go down into forces, okay? So the forces exerted on an object is what changes the motion of an object, right? So when we speed up, we have a positive net force, right? Because it's in the direction of the velocity. Right? If we're slowing down, we generally have a negative net force, and it goes against the direction of the velocity. Okay? So this would be a positive acceleration, and this one would be a negative acceleration. Okay, and so dynamics brings back in the kinematics equation. So remember those constant acceleration kinematics equations. Okay, all right. So generally, what you would have to do is maybe find acceleration using the forces, and then plug that into the kinematics equations, or find acceleration through kinematics equations and then plug it back in for forces, okay? And so here are two examples where we see that, where we work one into the other. So the first one, a drag racer goes from 0 to 60 miles per hour, which is 27 meters per second, in 2.2 seconds. How much force does the 75-kilogram driver experience during this acceleration? So unit one, we would have only done the first statement, right? So that's unit one. And that's what we're going to do here. Right? Here, when we're trying to find the amount of force, is what we're going to do on this side. So when we did unit one questions, remember, we wrote down our variables, right, to help us select a formula, right? And so here's how, remember, so we're going from 0 to 60, so 0 meters per second to 27 meters per second. We're going to do that in 2.2 seconds. And what we need is acceleration, right? So I'm going to write my final acceleration over here because I'm going to write it as one of my variables over on that side, okay? And so that's our question mark. Our frowny face is our unknown, or our displacement. And so if you look at it, there's one formula that doesn't have displacement, but all the other four, it's that V equals VO plus AT. I can do some cleaning up here. Right, so VO is 0, excuse me. And so then we can just solve this for A. And so it's going to be our final velocity over our time. And so it's going to be 27 over 2.2. Again, this will be a positive because we are speeding up. We're going from 0 to 60. So that means we're speeding up. So 27 divided by 2.2 is 12.3 meters per second squared. Okay, so there's our acceleration from our kinematics. And now we cross through the water, right? So we dive down into the water, and now this becomes the acceleration for our force problem. So force is our question mark, and they tell us that we have a 75 kilogram driver. Okay, so one thing to remember is that objects will be accelerated in the same rate as long as they are in the system. And so what force did they experience? We're going to do F equals ma. So 75 times 12.7. Okay, and so how much force did they experience? So that's not 12.7, 12.3 it should be. I apologize. And so that's going to be a force of 923 newtons. Okay, but again, here we were above the water, right? Here's our below the water. And then how do we cross into the water? Well, we found the acceleration, okay? Now, let's see a problem which goes the other direction, right? So where we find when we do forces and then we use it for our motion, okay? So Carol pushes a 25 kilogram wood box across the floor at a steady 2 meters per second. How much force does Carol exert on the box? And if she stops pushing, how far will the box slide before coming to rest? And the coefficient of kinetic friction between the wooden box and the wood floor is 0.20. Okay, so here's our water line, right? And so we're going to do our draw sum solve. So Fn, Fg, Carol's pushing force, which is F, and then here we have friction force, right? And so sum the forces, right? So this is going to tell us that the sum of the forces in the y direction is 0, Fn minus Fg equals 0. So Fn equals Fg. Okay, we don't necessarily have to worry about for the force because it says a steady 2 meters per second, right? And so that's just going to tell us that whatever she's pushing with is going to be equal to the kinetic friction. All right, and so it's going to be mg, so friction or force is mu mg, so that's going to be let's see, 0.20 times 25 times 10. So 0.20 times 25 times 10. So she's going to push with 50 newtons. Okay, so that's part A. Okay, now or the first question. The second question is now she releases the box, right? And so now it's a sliding object, and I'm going to do this shortcut. I showed you this to you guys the other, in class and the other day, where A is negative mu g. Okay, and so we're just going to do A equals negative 0.20 times 10. And so it's going to accelerate at a rate of negative 2 meters per second squared. Okay, and so now there we've crossed into the water, so our acceleration for our sliding object is negative 2 meters per second squared. Its initial velocity is that steady 2 meters per second. It's going to come to a stop. Okay, we're looking for how long or how far did it take, and our non-needed factor is our time. Okay, and so we have one equation where there is no time. V equals V0 plus 2a delta x, right? V0 or V is going to be 0, and we solve this for delta x, and so that's going to be negative V0 squared over 2a, so negative 2 squared over 2 times negative 2, right? And so you're going to end up with a distance of 1 meter is how far it would take for this block to stop. Okay, so that's all Newton's laws, okay, to include the application to focus on dynamics. All right, so now you should have everything you need to finish what you need to do prior to our test.